A relay. What is a relay? Relay is basically, it is electromagnetic switch. The circuit symbol for the relay. So how we represent a relay? A rectangular box which is showing an electromagnet and an open switch. What is the purpose of the relay? It is used to connect or operate high current circuit by low current circuit. Example, so you have AND gate. So for AND gate, when both inputs are high, 1 and 1, what will be the output? The output will also be high, because when both inputs are high, the output will also be high. So 1 and 1, it's 1. So if we connect a lamp here, so what should be the state of the lamp? 1 1 is 1, so state of the lamp should be on. But sometime the lamp, it should be on, but it remain off. What is the reason why the lamp will remain off even though the output should be high? Like for an AND gate, if we have an AND gate, when both inputs are 1, the output is 1, so lamp should work. But even the output is high, but the lamp is not working. Why the lamp is not working? Because this one is not showing the magnitude or amount of current or voltage produced. Maybe the voltage or the current which is passing through this lamp is not sufficient to light up the lamp. And for AND gates, for logic gates, normally the voltage and the current which is produced by these logic gates, it's a small voltage. So what happened? 1 and 1, the output should be 1. So lamp should be on, but what when we observe it is off. Why the lamp is off? Because the output current or the voltage is not sufficient to light up this lamp. So in that case, what we can do, we can connect a relay here. How we can use a relay? Example, we have this logic gate, AND gate is there. Then we connect a relay, electromagnetic switch. So we have a relay, electromagnetic switch, and with this second part of a relay, we connect the lamp and we connect a high voltage supply. So what happened? 1 and 1, the output of the AND gate will be 1. So when output is 1 means there will be a current which is passing, or output current will be there. When there's a output current, what will happen? Because this is an electromagnet means when the current is passing through it, it will behave like a magnet. So this electromagnet, as it is magnetized, this part of a switch is made up of iron, so it is attracted towards the electromagnet. So as it is attracted towards the electromagnet, the switch will close. As the switch will close, the high current start to flow through the second circuit. As the high current start to flow through a second circuit, what we will observe? We'll observe this lamp will be on, or this lamp will light up. So what is the advantage of the relay? Normally, when the circuits are operated at a low voltage and we want to connect a device which we need a high, which required a high voltage. So how we can connect these two things together, a low voltage circuit and a high current circuit, we can, or high voltage circuit, we can connect a relay between them. So what will be the advantage of the relay or the electromagnetic switch? So when the current is there, when the input is high, when the output is high, the current will pass through the relay, which magnetize the relay coil. As this part is magnetized, it will attract the piece of iron, which close the switch. As the switch is closed, the high current or high voltage in the second circuit will operate the device or the component which we want to work. If I directly connect this lamp to AND gate, when both inputs are high, the output should be high. Output is high, but that output current, this one is only showing the state. Like it is showing a state that it allow the current to pass. But maybe the current which was passing is too small. That is not sufficient to light up this lamp. That's why what we can do, we can connect a relay, because relay can be operated by a low current or low voltage circuit. Is it clear, the working of the relay? So example, we have say OR gate. So here we have the input is 0.1 ampere and this one is 0 ampere, means one of the input is high and the other input is low. What will be the result, the output for OR gate? If one of them is high, high means the there's current is there, the other one is low, no current. What will be the output of OR gate? When input is high and output is low, what will be the output of OR gate? So output will be high. Output high means it will allow the current to pass. So it will allow, like example, 0.1 ampere to pass. But as I connect a lamp here, so this lamp should be on. So if this lamp should be on, but when we observe this, it remain off. So as it remain off, what it shows that this 0.1 ampere is not sufficient to light up the lamp. It need a more voltage or greater current to work. The current is too low. So what we can do, instead of directly connecting this lamp to the output of the OR gate, we can connect a relay and connect a high voltage supply. Like here it is 0.1 ampere. So one of the input is high and the other input is low. For OR gate, so the output example is 0.1 ampere, it's high. We connect a relay coil. So when 0.1 ampere is there, this will magnetize, because current is having a magnetic effect as well. So this will magnetize this relay. as it will magnetize the relay coil. So a switch, the part of the switch is attracted towards the relay coil, and when you have this lamp connected to the high voltage supply, like example, say a 20-volt supply or a 40 or 220-volt supply is there, which can give you a more current, greater amount of current. So as a relay magnetize, this magnetic field attract the piece of iron. This is made up of iron. So as iron is also a magnetic material as well as a conductor, so it will close the switch. As it will close the switch, the voltage or the current is high here. Example, it is producing a 3 ampere. So this 3 ampere is sufficient to light up this lamp. So what will happen? This lamp will be on. If you use a button, it means you have to operate, like you have to switch on and off by yourself. It will automatically, according to the circuit, it will not work. Then you have to be there next to the circuit, and when you see the output of OR gate is high, then you will close the switch, and if output of OR gate is low, you will open the switch. So then you have to operate. It is electromagnetic switch. If there is a current in the circuit, the other switch, the other circuit will also work. Is it clear? The working of the relay electromagnetic switch. Any doubt in this part? This is electromagnet. Electromagnet means when there is a current, no, this is not the change in the magnetic field. Look, you have a wire which is turned around. This is the relay coil. So as there is a current passing through this coil, so what will happen? Using a right hand grip rule, you can identify the magnetic pole. When you catch the wire in the direction of the current, your finger shows the direction of the current, and the thumb will represent north. So north is towards right and south is toward left. So this part is behaving like a magnet. And what you have, the other part is a switch, and this switch, the component, one part of the switch is made up of iron. So as it is made up of iron, if you have a magnet and there's a piece of iron, so what happened? That piece of iron is attracted towards the magnet. So as this piece of iron is attracted towards the magnet, it will close the switch, and as it will close the switch, the current start to flow in the other circuit due to the other battery is there. So the device or the component will work.
Sir, I just entered.
This is a relay, the electromagnetic switch. Then we also use earthing. The earthing is mainly used for the, if you to avoid electric shock or electrocution. The symbol which we use for earthing, a wire, then horizontal lines. This is a circuit symbol for earthing. Example, and this is earthing is normally used for the devices which are having a metal body or the metal case, because if the appliance or the device is having a plastic body, plastic is insulated, it does not conduct electricity, so a person will not get an electric shock. Example, you are using a refrigerator. So this is a refrigerator and it's having a metallic body. So what you have to operate for working, so example, you have the live wire and the neutral wire. As you plug in, so as you plug in, the charges start to flow. The refrigerator is working this internal circuit as well for refrigerator. I am not drawing that. Now, if a person will touch, so what will happen? The person will get an electric shock. Why a person will get an electric shock? Because now he's a part of the circuit, so the current can flow. If the live wire is touching the metal body, so the charges can flow through that metal body and then passes through the least resistive path, which is the body, the human body as well. So to avoid this electric shock, what we can do, we can connect an earthing. So there is also another wire which is connected to the metal body, and that's known as the earthing wire. So what happens if there is a current in the live wire? Because two possibilities are there. One is the human body through which the current can pass, and another one is the copper wire. Copper is a good conductor as compared to human body. So what happens? Almost all of the current or most of the current will pass through a copper wire which is connected to the earth as compared to the human body. So to avoid an electric shock, we use this earthing wire. Is it clear? This already I discussed with you. The reason just it's also a part of the circuit component. That is why I discussed this again. This is a refrigerator which is having a metal body. So what happens if the live wire is in contact with a metal body? So a person, as a person touch, he will get an electric shock. So to avoid this, there is another wire which is connected to the earth, and we call this as earthing wire. And this earthing wire is connected to the metal body. So when there is a current in the live wire, which is the current in the live wire which is touching the metal body, so that current will flow from metal body to the earthing wire. So if a person is touching the metal body, he will not get an electric shock. Is it clear now? Now some questions related to electricity. This is February March 2020 paper. Electricity and magnetism mainly I will discuss with you. Normally from question 25 or 26 onwards, you will find electricity and magnetism. Okay, in this question, the diagram shows three different metal rods P, Q, and R, and inside a coil of a wire. Small iron nails are placed on a wooden bench. You can see small iron nails are placed on the wooden bench. The diagram shows the situation when there is an electric current. So means when we are passing a current, that is diagram 1. The diagram 2 shows the situation when the current is switched off. So when the current is switched off, still the nails remain in contact with R. Which row correctly identify the metal rods? What is the right answer here? Which row correctly identify the metal rods? Look, for first one, when you are passing a current, and if you are not passing a current, this material does not behave like a magnet. So if the material does not behave like a magnet, it means the P should be a non-magnetic material. Steel is a permanent magnet, iron is a temporary magnet. So when you check the first one, I want participation from everyone. So for first one, when you're passing the current, if you're not passing a current, it means the material, like when you are passing a current, there is a current, this material does not behave like a magnet. If this material does not behave like a magnet, it means it is a non-magnetic material. So it means this should be copper, because copper is a non-magnetic material. Iron, steel, nickel, cobalt, these are the magnetic material. When you pass, the current is having a magnetic effect, but that current is not able to magnetize this material. That's why the material is not attracting the iron nails. But for Q, when you're passing a current, it is behaving like a magnet. That's why it attracts the iron nails. For R, when you're passing a current, it is behaving like a magnet. That's why it is attracting the iron nails. So Q and R are the magnetic material. Then what about the nature of the magnetic material? As you switch off, this material is demagnetized. So which material is a temporary magnet, iron or soft iron? We can say it's a temporary magnet, where steel is a permanent magnet. So the correct answer is option A. Question 30. Which row describe the conventional current and the electron flow? Yeah, that's right. C is the correct answer. The
C.
conventional current, because the conventional current assumption is that it's from positive to negative. In reality, the electrons are moving from negative to positive. But in exam, if they say show the direction of the current, they always mean the conventional current. Until unless they ask in the question that mention which one is, like mention the electron flow.
Sir, in electrolysis, the electrons move from positive to negative.
In electrolysis, in electrolysis as well. Basically, in electrolysis, like example, you have a positive and the negative terminal, and you connect two electrodes. So from the negative terminal, electrons are coming out, and towards the positive terminal, electrons are moving. Electrons are
Okay.
attracted towards the positive and going out from negative. So it's the same thing. From negative terminal, it's out, and towards the positive terminal, it's in. It does not change. Why still we are using, look, the reason is that why conventional current is used till now, not the electron flow, even though conventional current is nothing. But because most of these laws in electricity are derived on assumption that the current is a movement from positive to negative. That is why they did not change the sign convention of the law. So still following those laws, because the statement of the law is correct, the only difference is the direction. So all of these laws of electricity are derived for positive to negative. That's why still we are using this conventional current. The student makes 4 resistors using a different piece of wire. The wires have different diameters and length. All pieces of wire are made up of same material. Which piece will make the resistance largest? Keep in mind, resistance is inversely proportional to area or diameter square, and resistance is directly proportional to length. So if you increase the diameter, it means you will increase the area. If you decrease the diameter, you will decrease the. So longer wires have more resistance and thinner wires have more resistance. So which combination will give the largest resistance? So B is the right answer, because when you decrease the diameter means you decrease the area, so resistance increases. If you use a longer wire, the resistance will also increase. A student is to determine the resistance R. She uses a circuit include a voltmeter and ammeter. Which circuit should be used? Voltmeter are always connected in parallel, because in parallel the voltage is same, and ammeters are always connected in series, because in series the current is same. So which circuit should be used to get the resistance basically by voltage? So D is the right answer. You can see voltmeter is in parallel to a component which we want to find the resistance, and ammeter is in series. So practically, if we have any kind of circuit, like example, if I say, so if I say I have 3 resistors connected in series. So I have 3 resistors connected in series and I want to find the resistance of this circuit. So to get the resistance of the circuit, I need the total voltage and I need the total current. So to get the current, I will connect an ammeter. And to get the voltage, I will connect a voltmeter in parallel to this series combination. That will give me the total voltage of this combination, and voltage divided by current, what we will get? We will get the resistance. So this is a practical way of finding the resistance of the circuit, is the voltage divided by current. The diagram shows a battery connected to 2 resistors. The 3 ammeters M1, M2 and M3 are connected in the circuit. Ammeter M1 reads 1 ampere. What are the readings of M2 and M3? So what are the readings for? Because they are all connected in series the current is same. So if this one read 1 ampere, the other one will also read 1 ampere. Throughout the circuit, the total current enter the circuit is always same as the total current leaves the circuit. A cell is connected to a parallel combination 2 ohm and 4 ohm. The current in 4 ohm is 1 ampere. What is the current in the cell? Current in the cell means the total current. So if we need a total current, we have the formula V is equals to IR. So we need the total voltage, we need the total resistance. So total voltage divided by total resistance will get the total current. This is one way. So this is one way, or what you can do, you can find. You can also do another thing because they are in parallel. So what we will do, first we'll find the voltage here. How to get the voltage here? So V is equals to IR. I is the current and R is the resistance. So 1 multiplied by 4, that's equal to 4 volt. So this resistor is having 4 volt because they are in parallel. So this will also have 4 volts. So both of them will have 4 volts. Now what about the current in this resistor? So how I can find the current? Current is equals to volt. V is equals to IR. So current is voltage divided by resistance. Voltage is 4 and the resistance is 2. 4 divided by 2, that's equal to 2 ampere. So 2 ampere is passing through the 2 ohm resistor and 1 ampere is passing through 4 ohm resistor. So what is the total current enter from the cell? The total current in the cell. If in one branch it is 2 ampere, the other branch it is 1 ampere. So what is the total current? You can use a ratio as well, but it is inverse ratio, like in reciprocal ratio, not the direct proportion. When resistance and current are inversely proportional, so if high resistance, low current, low resistance, high current. So what you can do, you can first find the current here in the 2 ohm resistor and the current in 2 ohm resistor and the current in 4 ohm resistor. So total current will be 3 ampere because the 3 ampere is passing. That's why D is the right answer. There's also another way to get this answer. Like after getting the voltage here is 4 volts. So we identify the voltage of this one is also 4 and the voltage of the battery is also 4 because all are in parallel. Now what about the total circuit resistance? So what is the total circuit resistance? It is product because they are in parallel. So if they are in parallel, it's product divided by sum. So 4 multiplied by 2 divided by 4 plus 2. So 4 multiplied by 2 is 8. 4 plus 2, that's equal to 6. So that will be equal to 8 divided by 6. 1.33. So 1.33 ohm is the total resistance of the circuit. You have the voltage. So you can find the current. Current is voltage divided by resistance. So it will be 4 divided by 1.33. When you divide, you will approximately get 3 ampere. So this is a second way of getting the answer. Question 35. Two inputs of NAND gate are joined together. Which truth table represent the action of this gate? NAND gate means the output of AND is inverted. So if we join, basically if we join the two input, it means, like example, if this is 0, this will be 0 and this is also 0. So 0, 0 for AND gate it is 0. When it passes through inverter, it will make 1. So if input is 0, the output will be 1. And opposite, if input is 1, so this is 1 and 1, 1, 1 is 1, but passes through inverter, it will make it 0. So basically, it will behave like a NOT gate. So when NAND gate, both inputs are joined together, it is acting like a NOT gate. When input is 0, the output is 1. When input is 1, the output is 0. The diagram shows a transformer that has an output voltage of 12 volts. So there's output voltage of 12 volts. The input is 240. Primary is having 1000. We need a number of turns of secondary. So use the formula Vs over Vp is equals to Ns over Np. So what's the answer? Correct answer after substituting the values? Vs over Vp is equals to Ns over Np. And first thing you can identify, look, it's a step down transformer because input is having 240 and output is only 12. So the number of turns of secondary should be less than number of turns of primary. So if primary is having 1000, so secondary should have less than 1000. So either A can be answer, B or C. It cannot be D because D is 20,000. So that's totally wrong. So when you substitute, so three answers are there like 12, 20 and 50. Now which one is correct? You have to check by substituting the value Vs over Vp is equals to Ns over Np. So when you substitute the value, you will find that C is the right answer. Three of them are possibility that it can be right, but one of them is the correct answer. D is totally wrong according to the working of this transformer. The diagram shows different particles moving through a magnetic field. Which particle experience a magnetic force acting out of the plane of the paper? So what you have to do for positive particle, use left hand. If you want to find the force on the positive particle in a magnetic field, use left hand. And for negative particle, you will use right hand. But the thing is, when the particles are moving parallel to the magnetic field, they will not experience force. They should move perpendicular or 90-degree. Parallel or anti-parallel, it will not experience. Like example, if this is a magnetic field and the particle is moving parallel or anti-parallel, like this is parallel to the magnetic field, this is anti-parallel. In both cases, the particle will not experience any force because it should cut the magnetic field. So how it can cut the magnetic field? By moving perpendicular to the magnetic field. So first, A and B cannot be an answer. A and B are totally wrong. Like it does not support that experiencing a force. So you're left with, yeah, the Fleming rule you have to use. If you are finding the force on the positive particle, you will use left hand. If you are finding force on the negative particle, you will use right hand. This part actually, this force on the particle in a magnetic field is also you will study in last topic, which is atomic physics. So this question is from atomic physics, but already you studied that the Fleming's left hand rule. So you can work out. So according to Fleming left hand rule, your first finger should point towards the magnetic field. So in this case, when you apply the rule, your first finger should point towards right hand side. Your second finger should show the direction of the particle, in which direction the particle is moving. So your second finger should point down. So where your thumb is pointing when you apply the rule. So first finger represent towards right, second represent direction of the particle which is down, and thumb is pointing, which direction your thumb is pointing? So thumb is pointing outward. Yeah, towards yourself. So if thumb is pointing towards you, what it shows that it is out, like because you are out of the paper. So when thumb is pointing towards you, it means it is out of the paper. But when you apply a right hand, because electron is a negative particle, so same rule is there, but instead of left hand, you will use a right hand. So again, the first finger, your right hand, Your right hand first finger should point towards the magnetic field. So that should point towards right side. Your second finger of the right hand should point towards the direction of the particle, which is down. And where your thumb is pointing, in the previous example, the thumb is pointing outwards. Your thumb, you apply a you will apply a right hand rule. Your first finger should point towards, all should be 90 degrees to each other. It's not, it's a similar, but instead of left hand, use the right hand. Your first, all should be 90 degrees to each other. So which direction your thumb is pointing, into the plane or out of the plane when you are applying a right hand rule? The same right hand rule, like same way you use the left hand rule for the force. Yes, Salman?
Sir, small confusion, sir. Last time we studied about South Pole and North Pole, right?
Yeah, that was about the magnetic effect of current. What is the magnetic effect of current? Means when a current is passing through a wire, and if you need a direction of the magnetic field, you can use that rule. So for left and right hand, like example, this was left hand rule. When you're finding a force on the wire or force on the particle in a magnetic field, you're using this left hand rule. First finger point towards the direction of magnetic field, second represent direction of the particle, and thumb is pointing in the direction of the force. When you're finding a force on the particle in a magnetic field, you will use right hand rule in the same manner as left hand rule. This part you will study in atomic physics, but because already you studied the rule, that's why I'm discussing this question. So first, in this case, for a right hand rule, your first finger should point towards south, uh, for a negative particle. So first finger is pointing towards the south, which is towards right, or the direction of a magnetic field. My second finger should point in the direction of the particle. The particle is moving downward. Where my thumb is pointing? Which direction my thumb is pointing? So that is into the paper. So if it is pointing into the paper, if you apply a, yeah, it is in, this is called into. Like when I apply a right hand rule for a negative particle, it is into. When I apply a left hand rule for a positive particle, it is out of. So basically this proton will experience outward force and this electron will experience inward force, or into the, so which direction it will experience? So the question was, which particle experience a magnetic force acting up out of the plane of the paper? So which of them is acting out of the plane of the paper? So in case of C, it is pointing out of the plane of a paper. This right hand rule, grip rule, is used to find the direction of the magnetic field due to a current carrying conductor. Is it clear?
Sir,
Yes.
where is the magnetic field then? Like, where is the north and south?
Where is the north and south? The direction of the magnetic field is from north to south. So basically, on the left hand side, you have north, and on the right hand side, you have south. They did not show that, they just represent the direction. They did not show the poles, but the direction of the magnetic field is from north to south. So this is a magnetic field. And the particle is moving perpendicular to the magnetic field. So you're finding the force which is experienced by the particle. So the rules, look, you have different rules.
Sir, so,
Yes, continue.
sir, we will not find. Okay, no, sir, it's confusing. That's clear.
Look,
I think I understand.
look, the rules are, first one is a right hand grip rule. Right hand grip rule, where we use, it is used to find magnetic field produced due to current carrying conductors like the wires. So the magnetic field, if we want to find the magnetic field produced by the current carrying conductor, we use a right hand grip rule. And this right hand grip rule is divided into two parts. It can be a straight wire or it can be a circular wire or a coil or a solenoid. So for a straight wire, if the wire is straight, our thumb will represent the current and fingers will turn in the direction of magnetic field. But if it is a solenoid or a circular wire, our fingers will turn in the direction of the current and the thumb will represent magnetic north. Then there is the Fleming's left hand rule. The Fleming's left hand rule, it is where it is used to find force on wire or positive charge moving perpendicular or 90° to magnetic field. So it is used to find force on wire or positive charge moving perpendicular to the magnetic field. And in this case, the first finger represent magnetic field or pointing towards south. The second finger shows the direction of the conventional current or particle. And the thumb will represent the force. Then there's another rule which is known as right hand rule. Then this right hand rule can be used to find two things. It can be used to find the direction of the current produced due to change in magnetic field, or it can also be used to find the direction of the force. So there are two ways which we can use. It is used to find the force on negative charge, which is moving perpendicular to the magnetic field, or it is used to find current produced or the direction of the current produced due to change in magnetic field. This is a revision part, but for each rule, I will make one session in which I will discuss each rule so you can have examples related to each. But this is just an overview because I'm discussing the MCQs right now. So I'm not going in detail, but next session, for each rule, I will give you example as well so you can have notes of that. So these are the rules which you have to keep in mind for magnetism and electricity: the right hand grip rule, Fleming's left hand rule and Fleming's right hand rule. And then according to this right hand also, first finger represent magnetic field, second represent the direction of induced current, and thumb is the movement of the wire or the force. This is February, March 2019, and I'll discuss electricity and magnetism questions with you. Question 28. The end of three metal rods are tested by holding end Q of a rod close to other ends. So end Q of a rod is placed close to the other rods as well. When end Q placed near end R, it is attracted. When it is placed at end S, it is also attracted. But when end Q is placed at T, it is attracted, and when it is placed near U, it is repelled. Which of the metal rods are magnets? Because for magnets, like poles repel and unlike poles attract. So
Rod 1 and rod 3.
rod 1 and 3. But what about rod 2? Rod 2 is made up of magnetic material, but it's
Material.
not a, yeah, it's not a magnet because it is an induced magnetism. Opposite pole will induce and it is always attracted. That's why rod 1 and 3 are the magnets. The metal sphere is charged by induction. Induction means, just a quick revision, what happened in induction. If we have a material, we want to make it charge. So we use a charge rod. So this charge rod will create a distribution. Electrons can move, positive charges cannot move. Then we connect an earthing wire which allow the charges to flow in or out according to the what charge we bring. And then we do another process which will make it permanent charge. So in the question, basically an object is charged by the help of another charge object. We call that as induction. So there are four stages, W, X, Y, and Z in this process. In which order are the four stages carried out?
A.
So what's the right answer? So first what we do? For question 29. Salman, you have a question? You raise hand.
No, sorry, maybe I forgot
Okay.
their hand. Sorry.
So what is the right order? I want participation from everyone.
A.
So in which order the four stages are carried out? A charge rod is brought near the sphere. So first we'll bring a charge rod. So first we'll bring a charge rod because that's a first we want to create a distribution of the charge. So to create a distribution of the charge, we should bring the charge rod. So when we bring the charge rod, what it create a distribution of charges. Then we connect an earthing wire. So when we connect an earthing wire, the charges will flow in. So there will be positive charges, but majority of them will be negative. And if you want to make it permanent charge, then what? Because we don't want the charges to flow back. If you remove the charge rod away, you can see for question 29, B is given. Why B is given? As you can see in the question, because if we remove, for question 29, why B is given here?
How, sir?
Yeah. First, the charge rod is brought near the sphere. That's we did first. Clear? Then we connect an earthing wire. When we connect an earthing wire, so the charges will flow in. So majority of them will be opposite charge. Then which one we should remove first? We should remove the earthing wire first, because when I remove the earthing wire first, the charges cannot return back to the earth. And then at the last, we will remove the charge sphere. If you remove the earthing at the last, it will not be permanently charged. Why it will not be permanently charged? Like example, you have a positive charge rod, you can bring negative as well. If you bring a positive charge rod, it creates a distribution of the charges, negative one side and the positive other side. If I connect an earthing wire, so when I connect an earthing wire, because the positive attract the negative charges, so majority of them will be negative. There are positive, but most of them are negative. Now, if I remove this charge rod first, so if I remove this charge rod first, the like charges, because majority of them are negative, so like charges repel. So what it causes? It causes the negative charges to flow back to the earth. So as the negative charges will flow back to the earth, again this sphere will be neutral. So it will not be effective technique. So what should be the order? First W means a charge rod brought near to the sphere. Then X, we connect the earthing wire. Then we should remove the earthing wire so that the charge cannot return. And at the last, we remove the charge rod. Is it clear now? Question 30, which electrical quantity is defined in terms of energy supplied in driving the charge around a complete circuit? Energy required to drive the charge, to move the charge around the circuit. That's the definition of EMF, electromotive force. Potential difference is how much work done by the charge or how much energy transferred by the charge. Both of them have a units volts, but the only difference, this one is how the charge get energy from the battery. That's known as the EMF. And potential difference is how much charge transfer energy when passing through a circuit. That's known as potential difference. Question 31, a student set up a circuit containing a battery of 2 cells and 3 lamps. Which diagram represent, what is the circuit diagram for this arrangement? So to understand the circuit diagram, just a small thing what you will do, you will replace these components by the symbols. Like first I have a cell, then also I have a cell, makes a battery, then this is connected to a lamp, and the other part of the lamp is connected to another lamp, and there's another lamp in parallel, and then the circuit complete. So it means the two lamps are parallel and one of them is next to them is series. So which one is the correct circuit diagram? So in this case, A is the correct. So the simple way to understand like which circuit diagram is correct, just replace the component by the symbols and you can identify the correct circuit diagram, because this is the same thing, like one lamp and then the second lamp is there. The two lamps are in parallel to each other, then connected to a battery or combination of the cells which make a battery. In which circuit does the lamp lights? Yesterday we discussed the function of a diode. I will just recall that. Diode, if the current is passing from the side of the play, the diode allow that. But if the current is passing from the side of the pause, the diode will block. So which of the circuit allow the lamp, does the lamp light up? Basically, which of the circuit conduct electricity? In that circuit, the lamp light up.
C. C.
I will, yeah, that's the right answer. C is the correct answer, but why not the other one? Look, if you check the conventional current, so this will block. This first diode will allow, but the second diode will block. So there is no current in A. For the second one, when you check this diode, both of the diodes will block. C is the answer, but what about D? When the current is coming, the first diode allow, but the second diode block, so the lamp will be off. But when you check C, both of the diodes, the direction of the current is from the side of the play, so they allow and the lamp will light up. Okay, each potential divider, yesterday I told what is the meaning of potential divider. It means when two resistors are connected in series, they divide the voltage. We call them as potential divider circuit. Each potential divider is placed in a circuit with a power supply. There's a power supply or voltage supply there. Which potential divider make the potential difference across the component Y increase when the light intensity increase? So basically, it should work with light. So C and D cannot be an answer. Why C and D cannot be an answer? You can see it's a thermistor. Thermistor,
Okay.
it only work with temperature. It does not work with light. Now, what happened? Yesterday we discussed for LDR, what happened when the light intensity increases? When there is more light, the resistance will decrease. It is inversely proportional. And we want, so what happened if there is more light intensity, then the resistance will decrease. So here the resistance decrease, in comparison, this component will have more resistance. So where the voltage will be higher, at X or at Y? For A, at Y the voltage will be higher, and that's a question only, that which potential makes the which potential divider make the potential difference across the Y increases. So A is the right answer. Why B is not correct answer? Because if more light intensity, smaller resistance, less resistance, here in comparison more resistance, so more voltage across X and less voltage across Y. But in the question we need more voltage across Y. That's why A is the correct answer. There are two inputs to the combination of a logic gate shown and one output. Which truth table represent the action of this combination? Can you identify from the circuit which truth table is correct? The way, if you want to identify, how you will identify, you will check the table. Like 0, 0, what should be the output of NAND gate? It should be 1 and then passes through inverter, so it make it 0. So first combination is right, but I have to check all, because it's not necessary that all of the combination. So if it is 0, 1, the output of this will be 1 and passes through inverter, make it 0. 1 0 it will also be, but when we say 1 1, when in both in 1 1 is 1, but this is a NAND gate, make it 0, and 0 will make it 1. So which logic gate is, which truth table is correct? Which of the truth table is according to the circuit? Look, input A and the input 2 are, when this one is 0, this output means this one, okay? And the two inputs are there. When both inputs are 0, 0 0 for NAND gate, for AND gate it is 0, but it's a NAND, it will make it 1. And that 1 passes through inverter, so that make it 0. So when both inputs are 0, the final output is 0. So first statement is correct. Now when you check the second statement, 0 and 1. 0 and 1, 0 and 1 is 0 for NAND gate, 0 for AND gate, but 1 for uh, 1 for NAND gate. And that passes through inverter, so it make it 0. So when input 1 is 0 and input 2 is 1, the output is 0. So second statement is also correct. When you check the third one, it is 1 and 0. 1 0 is 0 for AND gate, but passes through this NAND, so it will make it 1. And 1 passes through the inverter, so it will make it 0. So the third statement is also correct. When you check the fourth statement, 1 and 1, output of AND is 1, but because it's a NAND, so it will make it 0, and 0 passes through the inverter, it will make it 1. So it means truth table A is the right answer. The other truth table are not correct because one of them is the right answer. So you check when both inputs are there and the final output, this is matched with the combination of this circuit. Yesterday we discussed the fuse. The current in the kettle is 10 ampere and the kettle is protected by a fuse of 13 ampere. The owner of the kettle replaced the 13 ampere fuse with a 3 ampere fuse. What happened when the kettle is switched on? How the kettle will be damaged? If the fuse below, fuse is used to protect. So a kettle, the current is there 10 ampere. That's, and the kettle is protected by a 13 ampere. So it means 13 ampere is enough. The kettle can. So yeah, that's right. Basically, this is a, like, this is not a useful fuse, because when we say it is protected by a 13 ampere fuse, it means a kettle can work with 13 ampere. But what happens if you just place a fuse of 3 ampere? The fuse will melt and the kettle will remain undamaged. It cannot damage because 13 ampere fuse is used to protect the kettle. So it means the kettle can work with 13 ampere. So if even a current is lower than 13 ampere, the kettle will not be damaged. Even it might, the reason is it might be damaged. This is showing a possibility, but it not, why it cannot be damaged, because the fuse melt, so the current even is not able to enter the kettle. So that's why it is, as there is no current in the kettle, so it's not possible to damage the kettle. Like even there is no possibility that the kettle might be damaged. Which statement about the direction of magnetic field at a point is correct? What's the direction of the magnetic field? So magnetic field, it is the direction of the force on a south pole place as at this point. That's because the direction in which the south pole and it is a direction of the force on a north pole place at that point. No, not the rule. You don't have to use the Fleming's left hand rule is used to find the force on the charge in a magnetic field. But what they mean here in the question they are asking, direction of the magnetic field. Like example, if you have, if you are making if you have a magnet, so this is a magnet which is having magnetic pole north and south. We used to what is the direction of the magnetic field? We say the direction of the magnetic field is from north to south. Okay. Now, how we can work out the direction of the magnetic field? So the two options C and D cannot be an answer. That's about the electric field. So A and B can be answered. Now, which one of them? C and D is about the electric field, not about magnetic field, because the charged particle will have electric field. So C and D cannot be an answer. You're left with A and B. Now, in statement A, they're saying it is a direction of the force on a north pole placed at that point. Like example, if I place a north pole here, which direction this north pole will move? Inward or outward? So it will move same as the direction of the magnetic field. The north pole will move same as the direction of magnetic field outward. And same thing, if I place some north pole here, so which direction this north pole will move? So it will move towards the south. So basically, the north pole will move same as the direction of the magnetic field. So the which statement is correct? It is a direction of the force on the north pole placed at that point. Like when we place the north pole at any point in the magnetic field, it will move same as the direction of the magnetic field. So A is the right answer. Is it clear? Why statement B is not correct? Because if I place a south pole here, so the south pole will move opposite to direction of the magnetic field. In this case, the south pole will move towards, and here the south pole will move away. So the south pole is actually moving opposite to the direction of the magnetic field. A current carrying coil is placed in a magnetic field. A current carrying coil is placed in a magnetic field. Which effect does the coil experience? Like this is a current carrying conductor, a rectangular wire which is placed in a magnetic field. So whenever there is a rectangular wire, it will always rotate. Why it will rotate? Because one side it experience force in, other side it will experience force out, and this will cause a turning effect. So when you have a rectangular wire, it will always rotate in the direction of, because it create a moment or a turning effect. It can be clockwise or anti-clockwise according to the direction of the current. Here they did not mention the direction of the current. That's why we cannot say clockwise or anti-clockwise. But the idea is that whenever there's a rectangular wire, it will always rotate in a magnetic field. So these are the questions from February, March 2019. Any question related to the class today? Okay, so I'll end the session and share the recording with you.